So for the Choose Your Adventure lab, I'm gonna be simulating the motion of a lady on a swing. So we took a video, we went to a playground nearby and we took a video of a subject on a swing. And this is actually the motion that we are gonna try to simulate. So in order to extract the position data from Tracker, we basically use the seated height of the subject as our spatial scale. We know the mass of the subject, and that's going to be useful for when we run our simulation. And we know that the video was acquired at 30 frames per second, so we have a time scale. And we are going to choose the initial position of our simulation in a position where the swing is to the far left, where we basically assume that there is no kinetic energy at the initial point, so that the initial velocity is 0. So as I said, we imported the video into Tracker and we used our time and distance scale to extract the data. And here, as I said, and here you can see the data in X and Y position versus time. For the simulation, as a first approximation, we decided to treat the motion as the motion of a simple pendulum. And to do this, a good starting point is to use the angular expression of Newton's second law, that basically states that the torque is equal to the moment of inertia times the time derivative of the angular frequency. And in this case, the moment of inertia is ml squared, and the torque has this sinusoidal expression with respect to the angle that the pendulum makes with the vertical axis. In Python, we are going to calculate this angle theta, and we are going to use theta to obtain the x, y, and z component of the position of the pendulum. So here is the Python code where I imported the initial position as extracted from Tracker, the initial velocity, and I used this expression to obtain the angular velocity, the initial angular velocity, and the initial angle of the pendulum. Then down in our calculation loop, which is gonna go for the whole length of the video of about 19.5 seconds, we are gonna calculate the torque and insert the torque in the expression for the angular velocity, calculate the angle theta, and use that for the vector position of the ball. So let's run the Python code. And here we can see the motion of the pendulum simulated, and in this graph here, the blue line is the x position versus time, and the red line is the y position versus time. So we compared the simulated data that in this graph is in red, both for the x and the y position, versus the actual data, which are the black dots. And we can immediately see that we don't really get a good agreement, neither in the period of the simulated data versus the actual data, or in the amplitude of the data. So we decided to consider an improvement in the model by including both a periodic force and also the friction of the swing. And the reason of include a periodic force is that we can actually see that the subject on the swing periodically pumps the swing, and so it's adding force. And we are actually going to assume that this frequency f of the periodic force is the same frequency as the same angular frequency as the. So when we run the code with this new model, we actually don't see much of an improvement again. I mean, the period is a little better with respect to the previous model, but again, we don't really have a good simulation for the amplitude. Actually, if you look at the y position, you see that the actual data and the amplitude tends to increase with time, and this is not at all what the model reproduced. This disagreement with the data, we took it as a sign that the model we were considering was too simplistic. So we did some literature search to look at the actual motion of a swing, and we found this very interesting article on the American Journal of Physics about the pumping of a swing from the seated position, which is the actual case we are considering. And if we read the abstract of this article, what they do is the pumping of a playground swing from the seated position is modeled using a dumbbell consisting of 3 masses. The equation of motion of the system when the dumbbell is forced to rock back and forth is obtained, And when reasonable approximation for amplitudes are made, the equation of a linear harmonic oscillator with a driving and 3 parameter terms is obtained. So here I'm reporting the equation that it's actually obtained in this article, and we can see it's a much more complicated equation than the one I've used before. And here are just the expression of some of the parameters contained in the equation. So I've created a second Python code that actually consider this more complicated differential equation, and here is the result of the simulation for that case. And as we can see, the amplitudes are both in X and Y are reproduced much better than the most simplistic case that I considered earlier, and also the periods are much better. There is still some disagreement in the period and in the amplitude, however. So I conducted a little bit more of a search on the web to see if there was any model that would account for that. And actually, if you see, you can tell that this is, if you look at the subject is not a simple dumbbell, and also the pendulum is not linear. You see this kink here. So I found this other article of in Motor Control titled Pumping of a Playground Swing, in which a much more complicated system is considered. You see, this is not a simple dumbbell over here. I have not run further simulation with this model because I'm satisfied with the agreement I've achieved, but this the use of this model could possibly explain some of the disagreement I have found in my simulation. This is the end of the lab. Thank you for your attention.